Earth's atmosphere is a gas. Gas is a type of fluid. Fluids flow. That's why they're called fluids. And so they move around. We've already talked a little bit about some of the flow that can happen here, what we call convection. And so what happens is that sunlight heats the surface of the Earth, and then as the surface heats up, then it heats the air near it. The air near it then rises. When air is heated, it expands. So when it expands, it's less dense than the surroundings. Buoyancy is a property of fluids, so that if something is less dense, there's an upward force on it, and so it rises. As it rises, it expands more. Now, the way gases work, when they expand like this, because they're under less pressure, they expand, they cool off. Well, as long as it is cooler aloft than it is on the surface, then it might still be warmer than the surroundings. If so, it continues to expand and rise because it's still warmer than the surroundings. Now, at some point, if there's a layer of the atmosphere higher up that is warmer, it does not rise past that point. It'll kind of spread out. Now, the atmosphere has all different layers. We talked about the main layers of the atmosphere: troposphere, stratosphere, mesosphere, thermosphere, and then maybe the exosphere. But even within the troposphere, there's different layers of air that can happen. So masses of air, warm masses, cool masses, humid masses, all move around. And so sometimes you have a warmer layer aloft that keeps the circulation, this convection, from rising further than that. And other times you don't. Sometimes it'll rise all the way up to the stratosphere. And so these are the sort of circulation patterns you have on the small scale. These are weather circulation patterns. But there's also climatological circulation patterns, and that is that the weather in different parts of the world has certain properties that it keeps repeating, and that governs the kind of circulation that you get. So basic circulation, as I said, the ground heats up, the air rises, that displaces the cool air that's up, that sinks. Okay, now where the air is rising, it's expanding and getting cooler, which means it tends to have less ability to hold moisture. So clouds tend to form there. Where the air is sinking, then it's compressing and getting warmer. And so in that case, you typically don't get clouds because you're actually able to hold more moisture. Now, on the surface of the Earth, where the air tends to be going up, you're getting less air here. And so that means that you have less air pressure, and so the pressure is lower. So this is typically a low pressure region. Where the air is coming down, it's compressing the air, and that's typically a high pressure. So typically, if you look at weather maps, where there's a big L for low, that's where the air is rising, and you're more likely to have clouds near there. Where there's a big H, that's where the air is sinking, and that's where you're typically going to be more clear. Now, often the temperatures would also be, for example, in the summertime, where the air is sinking, it compresses the air and gets hotter. So a big high sitting over Texas in the summer tends to make it hotter, and it's clearer, which means more sunlight coming in. Whereas the other thing that can happen in the winter is that the air can actually become just very cold and very dense, and that makes it high pressure. The other thing is air tends to flow from high pressure to low pressure. So typically air is flowing into the low and out of the high. So that means near the low it tends to be windier than it is near the high. Near the high, the air is coming down and spreading out, and so it typically is much more calm there. Again, you notice that in our area where there's a big high sitting over Texas, and it's typically very calm, not much wind blowing, and hot and miserable in the summertime. In physics, we talk about something called the Coriolis effect. The Coriolis effect is something you notice with a spinning body. And that is that if you have a spinning plate or a merry-go-round or something, and you have something that you throw straight outwards from the center, so it's going to go straight outwards, then it looks just fine if you're looking from above. But if you're sitting on the merry-go-round at like that red dot, you're sitting on the red dot, it looks like that thing is curving off to the right instead of going straight. So this is a perceptive sort of thing. But as far as you're concerned, sitting on the merry-go-round, it looks almost like someone pushed it to the right. Okay. Likewise on the Earth. Okay. If you have something here that's going around, Earth is spinning, and so you throw something due east. It's actually what happens is because you're throwing it faster than it needs to be for that particular latitude, then it's going to end up going it looks like it goes to the right, okay, towards the equator. If you were throwing in the other direction, it would be going too fast for that latitude and sort of spin outwards and kind of go to the right also. You throw it towards the equator, and what happens is the equator actually has to go around faster, so it's going to lag behind and go this way to the right. And you throw it to the north, it's also going to go to the right because the ground actually moves slower to the north than to the south. Okay, think about how a sphere works. All parts of it take the same length of time to go around, but closer to the equator it has to go faster because it's a bigger distance around. So it looks like everything is pushed to the right. So everything gets pushed to the right. In the southern hemisphere, it works the other way. Everything looks like it gets pushed to the left. Actually, something that comes into play in artillery. So if you shoot artillery rounds a long distance, then you have to realize in the northern hemisphere it's going to land to the right of where you're shooting them. In the southern hemisphere, it's going to land to the left of where you're shooting them. And so this is something that's just something you take into account. Well, remember, for low pressure regions, air is flowing into the low pressure regions, but it can't just go straight in because it's going to feel like it has a force pushing to the right. And so it's going to spiral in. So rather than going straight in, it's going to be pushed off this way, and so that means it's going to spiral in like that in sort of a counterclockwise fashion. So air flowing into a low is going to spiral in a counterclockwise fashion in the northern hemisphere and in a clockwise fashion in the southern hemisphere. So examples of this would be a hurricane. In a hurricane, the air can't just go straight in, it gets pushed to the right, and so it spirals in, in a sort of counterclockwise fashion. Likewise, very low pressure region here, air is being pulled up really rapidly, and so it spirals in a counterclockwise fashion. And so, again, that gives you these big winds because you end up having, as you spiral in like that, you have to go a longer distance in the same length of time, and so that means it's going faster. So this intensifies the wind speed. And so hurricanes and tornadoes are examples of this. All of these are a generic type of storm they call a cyclone, which is a low pressure region, air flowing in. Cyclones, the air rotates in a counterclockwise fashion in the northern hemisphere. In the southern hemisphere, everything gets pushed the other direction, so cyclones rotate in a clockwise fashion. So that's one reason these storms can never actually cross the equator, and that is that as they're moving, then what's happening is that the air has to rotate in different directions. Again, this is a radar image of a hurricane going up into North Carolina a number of years ago, and you see the rain bands, and the rain bands are being pulled around in a counterclockwise fashion. Now, these are all weather events, so they are localized to a particular cyclone. Turns out that Earth's atmosphere as a whole moves, and that gives climatological effects as well.